And the first one we're going to talk about is the greatest common divisor. So the greatest common divisor is also a binary operation, although we don't usually think about it that way. But the greatest common divisor is what it sounds like. It's the largest number that divides a pair of numbers. Greatest common divisor, x, y, the integers. The greatest common divisor of x and y is the largest number to divide both x and y. Now, technically, I'm lying to you. There's a little bit of a case where you need to be careful here. We'll come back and fix it once we've covered it. But for instance, 1 divides every number, right? So every number has at least one divisor. And then you just pick, okay, these are the divisors of this, these are the divisors of this, and here's the biggest. So the GCD of 2 and 6 is, what about the GCD of 3, and what about the GCD of 6 and 10? What about the GCD of 3 and 7? Y'all are warmed up now, right? What about the GCD of 0 and 8? 8. So 8 divides 0, right? Yeah. 8 divides 8, right? Is anything bigger than 8 divide 0? Yes. Is anything bigger than 8 divide 8? Okay, so 8 is the largest number that divides both 0 and 8. What about the GCD of 5 and 5? 5. Y'all see how this is a binary operation? What about the GCD of 0 and 0? That's a problem. Technically, this isn't a binary operation because I have one case where I can't work around. So I should really say here that x and y are not both 0 or some kind of special condition. It's totally okay to have negative numbers, by the way. And you could weasel your way out of this by just defining a special case and work around it, but we're not going to get into that. This is a concept you've seen before, right? Well, this idea was known for a long time, so it's very important. And the question is, we're going to start here with something, but this is called the division algorithm. And even though it says algorithm, it's not actually an algorithm, it's actually a theorem. So suppose you have 2 integers and the second integer is required to be positive. Then there exists unique integers Q such that R is between 0 and B, and A is equal to B times Q plus R. So like, let's look at A equals 17 and B equals 7. I'm saying 17 because the main reason we prove the division algorithm is to establish another condition, or another process called the Euclidean algorithm. So the Euclidean algorithm is an honest to goodness algorithm. And whenever you talk about algorithms, you should talk about what the input to the algorithm is and what the output is. So our input is going to be 2 integers, A, B, and Z. And we will require here that one is positive so that we don't end up with some kind of 0 nonsense. And the output will be the GCD of A and B. And the way it works is this. You're going to use the division algorithm and you're going to write A equals B times Q plus R. And then you're going to take this B, I'm going to call this R sub 1. Take this B and this R sub 1 and you're going to make it be the new A and B. Now you're going to write B and let's call this Q1. Now you're going to write B and you're going to write it as R1 times Q2 plus, which you can do because R2 will satisfy the condition on here and everything works out. And then you're just going to keep doing that. You're going to go, okay, well, R1 is equal to R. You take this and you shift it over. R1 is equal to R2 times Q3 plus R3. And you're going to keep doing this until eventually you get R sub n minus 1. You don't know what this will be, but is equal to R sub n minus 2 equal to R sub n minus 1 Q sub n plus 0. And whatever this number is the GCD. So it seems really abstract until you do it a couple of times. But basically you're taking your divisor, your remainder, you're shifting them over, you're finding a new remainder, shifting the remainders over, finding a new remainder, shifting the remainders over, finding a new remainder, shifting the remainders over. Would you give me numbers that we could use to investigate? What's that? Okay, so A equals 48 and B equals 5. I want to say 5. All right, we can do 512 in a minute. So 48 is equal to 5 times 9 plus 3. 5 is equal to 3 times 1 plus 2. It's 5 and it's 3, and make it the new object of my division algorithm. Now, what would the next step be? Now, what's the next step? So the GCD is 1. whatever the last non-zero remainder is. When you get to zero, back at the previous step. So this establishes that the GCD 48 and 5 equal to 1. This establishes the GCD of 48 and 5 is equal to 1. And this isn't too bad if you believe that you can divide and find remainders, which we can. If B is bigger than A, you have to switch it. Start with 512 equals whatever times 48. But you do this. So let's look at one where we know the answer. What's the GCD of 2000? It's 2. All right. How do we let's show that? So we go 2000 equals 2 times 1000 plus 0. Well, this was the last remainder before the 0. So it works out just fine. There's no trick there.